Okay. Hello. Thank you for coming. I know it's the last session of the day, but I hope you have some energy left. My name is Adam Warski. I work for Software Mill, and I would like to talk a bit about modularity. So first there will be maybe a bit philosophical part on the various characteristics of module systems, so what could constitute an ideal module system. And then there will be two practical tools which you could use today to hopefully improve modularity of your programs. So apart from that, what maybe you could take out of this talk is a question. There's a lot of new languages. There's like almost a new JVM language every week. And if it's not JVM, it at least compiles to JavaScript. So when you look at these languages, when you read about these languages, and even when you compare these languages, what we most often look at is, for example, things like, hey, I can sum up a list of integers in one line instead of 3 lines, or this takes 10 characters less to write. So, of course, I'm exaggerating a bit, and concise syntax is important. But what you don't see are things like, hey, with this language, it is easier to write big modular programs, or this language makes it easy to develop large programs which can be split into modules, and these modules can be reused and so on. So maybe we should focus a bit more on the modularity side. So it may be less exciting than all those nice complex language features which some of the new languages have. But maybe it's better to have simpler languages, but to develop the modularity side a bit. Okay, so a bit about me, so you know who I am. So as I said, during the day, I'm coding mainly Java and Scala at Software Mill. Software Mill is a great software house. We are based in Poland, but we have clients all over the world. We are a fully distributed company, and also everybody is a CEO in our company, which is an interesting topic in itself, but not for this presentation. So in the afternoons, I just play around, duplos, Braillons, and so on. And of course, the evening is the perfect time to have some free time finally. And when you have free time, of course, you can spend it, for example, blogging or doing open source. So as for open source, I'm the author of Hibernate Anvers. It's an entity auditing module. It's part of Hibernate. I also work on some other projects like ElasticMQ, Veripacks, and Macquarie. Veripacks we are going to see in this presentation. And I also write a blog, which I invite you to read. I think sometimes I write something interesting, maybe, so please take a look. Okay, so the plan for the next 50 minutes, I think I roughly covered it. So first, there will be the characteristics of modules, and then we look at Veripacks, which is a Java Scala library, and at some of the modularity features of Ceylon, which is one of the new JVM languages. Okay, so let's start by thinking what a module could be, right? Because we often talk about modularity, but what does it mean that something is a module? So I guess everybody will answer that question differently, but here are some candidates. So maybe a module is an OSGi bundle, right? So it's a jar with some meta information. Or maybe it is a jigsaw, something, I'm not sure what the jigsaw things are going to be called, maybe modules or maybe something else. But that's quite similar to the OSGi bundle thing. Or maybe a module is a Maven build module, right? So in Maven you can have multiple sub-projects or modules, right? Which can depend on each other. Same in SBT or in Gradle. So these are kind of modules as well. In JUice, the dependency injection framework, we also have modules. So the modules in JUice are a bit different, right? So in a module in JUice, you specify which class implements which interface, right? So you specify the bindings, which are then used to instantiate the objects and to actually do the dependency injection. And that's called a module as well. Finally, we have, for example, also the Ruby modules. In Ruby, a module is just a bunch of methods which you can include in a class. So it's kind of a mix-in, which you can do. So the types of modules are quite different. So maybe let's look in the dictionary, right? So there's a couple of definitions. The one that we are most interested in is the second one, I guess. So a module is a part of a computer program that does a particular job. So again, that's, of course, I will guess that's a definition which everybody would agree with, but it's a very broad term, right? So we are not going to deal with space vehicles, which are interesting as well, but modularity is obviously more interesting, and that's what we are going to focus on. Okay, so as I said, the things that are covered by the word module can be very broad. So I think we can talk about something like a modularity continuum. So we can get modules in different sizes and shapes, right? And quite often the bigger modules can contain the smaller kind of modules, and this forms kind of a continuum. So let's look at an example continuum that we might have in Java. So that's, of course, my take on the subject. Yours could be a bit different. But let's see how we could approach this. So at the bottom, so the smallest kind of modules in Java or Scala as well are classes, right? So you don't traditionally think about classes as modules, but in fact they are a part of a computer program that do a particular job, right? Especially if we adhere to the single responsibility principle, right? Each class has one specific responsibility. It's a bunch of methods, maybe some state, and you can think of it as a module. Why not? So as an example, I'm going to use a banking system. So for example, we can have a class which adds money to an account. We can have another class which withdraws money from an account, and so on. So if we if we have a bunch of such classes, they could form a package. They could be modules in a package, right? So the second stage would be packages. And again, we can have various packages. And the packages also usually have some specific responsibility. So they're also a part of a computer program that does a particular job. So we can have a package which allows you to do operations on a user's account, right? So this will contain our add and withdraw money classes. We can have another package for listing an account history. We can have yet another package for money transfers. And these all will be modules or part of build modules, right? So we can bundle these packages into jars. So a build module usually results in a jar, right? And so we can group some packages, put them into a jar, and again, such a build module should at least have some specific responsibility, right? So for example, we can have a build module or a jar for operating on accounts. So this will contain the transfer packages, the add remove money packages, and so on. We can have another jar or another build module for authentication or for creating accounts. And these build modules will be in part modules of a project, right? So a project, this might be an account management backend project, right? And this project will be deployed somewhere on an application server, and this will contain the build modules that we talked before. We could have other projects, like a UI project, a mobile UI project, and so on. And if you take each of these projects will be part of a bigger system, right? It will be a module in a bigger system. And again, we can have various systems. We can have a bank credit system. We can have a banking account management system, right? So I think at least in some way, you can always think about each of these stages as modules of the higher stage, right? So now there are a couple of questions here. For example, are all of the stages enumerated here? Should all of these stages be really distinct? Because each of these stages, like classes, have different syntax for defining classes. There's a different syntax for defining classes and a different syntax for defining packages. So maybe we should have more steps in our continuum, or maybe we should merge some of them. For example, packages and build modules. Okay, so let's now look at some of the characteristics that module systems can have. Some of these module systems, which I talked before, each of these module systems can be characterized by these traits. Okay, so like a universal property of each, at least decent module system, is grouping code, right? So we want a module, whatever that means, to group code, right? So we want it to group a code that, like in a comprehensible chunks. So we want to be able to understand what the code in the module does. Also, the module should have a specific responsibility or single responsibility, but what exactly having a single responsibility means, that could be like a very wide range of things, right? It depends on how general our language is. So we can have a single responsibility, which is a whole project, or we have a single responsibility, which describes a class. So, in fact, the single responsibility principle is very flexible in depending what language do we use. So here we also get things like namespacing, isolation. This can be also runtime isolation. Okay. So second trait, reusable, right? If we have a module system, we usually want the modules to be reusable in some way. So this can be reusable across one system. So sometimes you want to have a module which is like an inline module. It's very specific to the domain. So maybe it will be reusable only in one system. Maybe it's a more generic module, which we would like to reuse in multiple systems. Or maybe we have industry standards. So like JEE, it is an industry standard, right? And we can reuse the implementations, so the various implementations of the various specifications in various systems. So you can think of these implementations as modules as well. So jars are a good example here, right? You can reuse jars. You cannot really reuse, for example, packages. You cannot take one package and let's use just and use this one package. You have to take the whole jar. Okay, abstraction. So if we have a module system, we would like it to provide us a way to hide implementation details. So we would like a way to have a way to define what is public and what is private, right? So that's obvious, for example, in classes. We have private and public methods, right? It's not possible. It's also possible in the packages. We have the public class. We can have a public class, a package protected class, and so on. With jars, it's not possible, right? Because the content of the whole jar is always visible. You cannot constrain what is visible inside the jar. However, if we use OSGi, we gain abstraction because we can export only some packages from a jar. Also, another possibility that we have here is to hide not only the details of what can be accessed, but how. So, for example, in a juice module, right, we also define how the objects are wired together. So, in a juice module, we have some more information apart from which interfaces implemented by which classes. We also have some information on how these classes should be used together, at least in a default setting, right? So there's also some information which we may want to abstract from our clients. Interfaces. That's, I guess, quite an obvious one. So we would like our modules to define a way how we could define an interface, how we could define the data structures that the interface accepts and returns. And we would like to be able to make multiple implementations of our interfaces, right? So obviously classes are a very good example here. We have interfaces in Java, we have traits in Scala. We can implement these interfaces multiple times in different ways. Packages or jars are a negative example. You cannot have an interface and have a jar implemented interface. Same for OSGi and so on. JEE is a good example as well, right? JEE is in fact a set of interfaces which can be implemented by multiple different implementations, and each of these implementations is kind of a module which we can use through the JEE interface in our code. a very important property, composability. So are we able to create big modules from small modules, right? So can we stack our module, our modularity implementation, right? So this can be hierarchical. It doesn't have to be, for example, packages aren't really composable. You cannot compose a package out of any other packages, right? The same, you cannot compose multiple jars. You can compose multiple classes, for example. Okay, and also so with composability, we would also like our module system to be scalable, right? So, well, that's a question, in fact. Do we want that? Do we want to be able to define small modules the same way we define very big modules? Right? So do we want to have the same way to define, if we have such a way, right, then we can have small modules, compose them into bigger modules, and so on, right? So with classes, packages, build modules, and so on, we have various ways to do it. But maybe it would be nice to have actually a single way to define the modules and grow the concepts. Okay, last but one, replaceable. So we usually want to be able to somehow swap implementations, especially if we have interfaces. But if we have modules, we want to take out one module and put another implementation in its place. So in OSGi, you can, for example, do it at runtime. Right? So if we know that a jar implements some set of interfaces, we can take out this OSGi bundle, we can put another one, yeah, it can provide some services and so on. It can be also done at load time, as with JEE, or at build time even. With classes, you cannot really swap class implementations so easily, unless you're using a dependency injection container, which is kind of the point of using a DI container, right? So you can, when you bootstrap your whole system, you can replace the classes. Finally, we have meta information. So very often module systems give us some way to express dependencies, right? So we want to say that a particular module depends on other modules. We may also want to say that a module has a specific version and that we depend on specific versions of other modules. But that's not always the case. It is certainly true for OSGi or Maven modules, right? But not so much for classes. We don't really version classes, or we don't version packages. But we can express dependencies with classes, for example, through constructors. And we may also want to have some tools to verify that our meta information is correct. Okay, so these are the requirements that I was talking about. It's a sum list. It probably can be extended in some way. So what do we do now, right? We have a set of requirements that we would like our ideal module system to have. So there's a couple of things we can do right now. We can start creating a new revolutionary language, but we have only 42 minutes left, so that may be too short. So let's look at some alternatives. So the first practical alternative is looking more closely at packages and at a tool called Veripacks. So we are going to zoom in into this level in our continuum. So yeah, packages, I guess everybody used packages at least once in their life, if they are a programmer, of course, Java, Scala programmer. So packages, they are very great. They are a very good tool for namespacing, and that's how we usually use them. If you look how the tools use packages, so for a Java compiler or for other tools, package names are just simple string identifiers. By convention, we use the reverse domain name convention, right? We use dots to separate the various components in the package names. But for tools, the package names are just simple string identifiers. So the tools don't really have any parent-child relation. They don't know that, like, if we look at the first package over here, right, and the second one, we kind of understand that the invoicing package is a sub-package of finance, and that probably it contains that the finance package is somehow a parent, right? So, and that's in fact how IDEs present us packages. They present the packages in trees. So somehow we use packages as if there was a hierarchy to the packages, but the tools only use them as simple identifiers. Okay, so now let's look at classes which come in these packages. So, yeah, the question is, are all classes equal? And I guess the answer is obviously not. However, by default, when you create a new class in an IDE, for example, usually, unless you change your settings, this class will be public, right? So if you don't do anything, you will get all classes, you will get only public classes in your packages. In Scala, in fact, the default is a public class, right? You have to explicitly annotate it to make it not public. So now when we look at such a class, which has only public, at such a package, which has only public classes, we can start to think like, and ask questions like, what is the main class in the package? Or what is the responsibility of the package? And it may be not so clear, like, right? We may have to look at all these classes and actually see which one is used from other packages and so on. So there's a pretty simple solution to that problem. We can, by convention, try to make one public class per package, right? And we can make the other classes package protected. So then this kind of forces us to have packages with a single responsibility. And when we look at such a package, we know what's the main entry point to the package. So if we want to use that functionality, we more or less know which class should we use. We could also, when we test, this can in fact help in testing the package. We can only test the main class. But what if we want to grow that concept, right? What if our functionality gets big? Well, then we usually extract a sub-package or a child package. But then, to be able to actually use classes from the sub-package, we have to make them public, right? So we lose our careful design to make only one class per package public, and somehow annotate that the other classes only help in implementing that main functionality. So if we extract the sub-package, we have to do it in some other way to specify our intent. Okay, and that's the problem that Veripacks tries to solve. So with Veripacks, the name comes from verify package specifications. Using annotations, you can specify which classes are exported from a package hierarchy. So that means that if you export a class, it will be the only visible class from the whole tree of that package down. So you can export both classes and child packages. So if you export a child package, you only export what's in the child package. And all the parent-child relationships that we intuitively have when we look at packages are respected here. So Veripacks is mainly suitable for use in application or in project modules. So there's no versioning information and so on. So it will be mostly useful for modules that are forming a single application. Okay, so an example. So we have 3 packages here. They have very boring names. I'm not very good at example names, I guess. And so we have the P1 package, right? It has 2 classes, A and B. And we can see that class A has an export annotation on it. So that's, of course, a bit of an imaginative syntax, but I hope it's clear. So class A is annotated with at export. Class B has no annotations. And in the sub-package, so we have class C is in the sub-package of P1, right? We have class C, which again has no annotations. So now let's see what happens when we try to use code from package P1 in another unrelated package, P2, right? So of course we can create a new instance of A. We can access A without problems because it is exported. We cannot access B because it is not exported, and we cannot access C because the only class that is exported from the hierarchy of P1 is A. Okay? So now what could we do if we wanted to use C? Well, we could export both C, and then P1 would have to re-export the sub-package. Okay? So how does exporting work in more detail? So by default, if there are annotations, everything is exported. You can export a class. You can export two classes. Well, in fact, you can export any number of classes by simply annotating them. You can export a child package by annotating the package. And you can annotate packages in a special package info.java file. Or you can mix it in any way. So you can export both a class and a child package and so on. And what is important is that these operations are transitive. So if you export a class, you actually hide not only other classes from the same package, but also all other packages. So how can you run Veripacks? Well, there's a simple builder interface. You can, for example, a simple builder class. So you can, for example, run it as a unit test. So you have to tell Veripacks what is the root package that you want to check, and then you just run the checks, and it will read the code from the class path and verify if the annotations match the actual usage. Okay, the second part of Veripacks is concerned with importing. Importing is also transitive, as all operations in Veripacks are transitive. And there are two use cases here. So first of all, you may want to have a package which can be used only if it is explicitly imported. Right? Before, you could use classes from a package as long as they were exported, but there were no constraints where these classes could be used. So importing is a way to constrain this. So if you want a package to be used only in specified places, you can annotate it at requires import. And then at the usage side, you have to explicitly import that package. So that could be both a kind of documentation, saying that this package uses some other packages, right? And it can also be verified by Veripacks. And you can use that for importing third-party libraries. So as an example, let's look at the implementation of Veripacks. So Veripacks uses Object Web to read the class metadata. So it uses Object Web is a library for parsing class files and reading annotations from them and so on without actually loading the class. So the constraint that I want to express here is that the Object Web package should be only used inside of the veripacks.reader package, right? So it's kind of like adding a dependency, a third-party dependency, only to a specified package. Okay? So what I can do is I can annotate the reader package with the @import, right? Where I'm importing org Object Web to the veripacks.reader package. And so here you also have an example of how we can annotate packages in Java. You create a package info file and to do the imports there. So when you want to run it, you have to specify that the org Object Web can be only used if explicitly imported, right? And this brings us to a subject of build modules. So build modules are very useful when you want to create a jar, but at least in my experience, they are often used also when you want to, like in other cases. For example, we want to isolate a part of code, right? So we want to have like the want to specify that this part of code is separate from our project. So we create a build module. And very often the name of the build module actually is the same as the name of the package. We may have an API implementation split, right? So we create an API build module, which other modules depend on. So when we want the functionality to be used through that API, and then we create yet another build module, Maven subproject or whatever, which actually implements that API. We may want to add a third-party library only to a part of the code, right? So that's the scenario that we've seen a moment ago. We may want to group code with similar functionality, and so on. However, build modules are pretty heavy. Well, in Maven, you have the whole big XML that you have to define for each build module: the project ID, the artifact ID, the version, the dependencies, and so on. Even in SBT or Gradle, that's much easier, but you still have to create a separate directory structure. You have to name that module somehow. And so I guess that actually creating a build module is kind of a big decision, and we may actually be reluctant to in doing that, because it's not that easy as creating a new class, for example, right? Also with build modules, there's sometimes the problem that to actually make two build modules communicate, you have to create a third one, which is like a common module, common something, right? So, of course, Veripacks can help here in replacing some of the build modules. I don't expect you to actually read what's in there, but on the left, you have an example project with 3 modules. The modules are reporting, frontend, and domain. And the project on the left uses build modules for separating these 3 project modules, right? On the right, Veripacks is used. So we only have packages. We have some import, export annotations, and it requires import. And as you can see, the resulting structure is much smaller. These 2 projects are on they are on GitHub, so you can take a look how you can create, like, for example, we have here the domain module, which is a dependency of the front-end module and of the reporting module, but the front-end and reporting know nothing about each other. So with Veripacks, with the exports and with the imports, you can actually replace some of the usages of build modules and get a more compact structure. Okay, so other benefits of replacing build modules. So, for example, you don't have to think when a functionality is big enough to create a module, right? Because it's always a problem. When do we jump from a package to a build module? It's not so obvious. It's much easier to share test code, because we can have test code that is shared among 2 packages easily. Having test code which is accessible from 2 build modules is not that easy. Also refactoring is much easier. Changing the name of a package, extracting a sub-package, and so on, that's like normal day-to-day operations, right? And however, renaming a build module is, or introducing a new one, is a much heavier task. Okay, so to sum up the packages plus Veripacks approach with our traits that we defined before. So of course you can, with Veripacks you can group code. What you get is modules which are reusable in some way, right? You can depend on other packages, but you cannot really, again, take a package in itself out of the jar. Veripacks provide abstraction via the export method. There's still no way to define interfaces and a way to implement, so a package still cannot implement an interface. You get some composability through transitivity of the packages, right? So we can compose bigger packages out of smaller packages, but it's not like you can compose a big package out of any smaller packages. These smaller packages must be child packages. And you get some meta information, like you can express dependencies with @import, but you don't get any versioning. Okay, so now let's look at the second tool, Ceylon. So Ceylon, if you go to the website and read what actually Ceylon is, so the first sentence says that it is a language for writing large programs in teams. So that's kind of what I was saying in the beginning, right? So that it tries to emphasize the words large and teams here. So that it makes it the main goal of the language to actually be able to write large programs, which may be promising. It's a cross-platform language. It compiles to JVM and to JavaScript. It's statically typed. It has, so from the interesting things in the type system, for example, it has union and intersection types. So that's quite a new concept, I guess, in the JVM languages. There's also a new language by Martin Odersky, who is the Scala creator. So the language is called Dotty, and it also contains union and intersection types. So I guess the concept kind of catches. Ceylon is like almost all languages now an object-oriented functional programming mix. It has types of metaprogramming, which is also quite interesting. It is developed together with an IDE. Unfortunately, the IDE is Eclipse-based, but nobody can be perfect. And today, actually, it was announced that version 1.0 is available and can be downloaded. It's open source. And also, of course, what we are going to talk about here, it puts a big emphasis on modularity. So the Ceylon modules are a bit similar to what OSGi or Jigsaw, I think, may offer. So we are moving now a level higher from the packages to build modules. So as I said, they are similar to OSGi, but the modules are part of a language, and they're like a construct in the language. So first, only a little bit of Ceylon terminology. So in Ceylon, things can be shared or not. So, and things are program elements like classes and class members and packages. And in fact, module dependencies, as we will see further on. You can think about shared as the equivalent of public in Java. So we have three basic modularity concepts in Ceylon: modules, packages, and classes. So classes are the smallest one. Classes are grouped in packages, and packages are grouped in modules. And these are three distinct concepts. They have three distinct syntaxes for defining them. Classes are mostly similar to Java: methods, state. Again, a shared class is a public class. A non-shared class is not public. Now, packages. Packages can be described in a separate file with metadata. The file is called package.ceylon, right? And the file should be put right where the package sits. So we can, this file can contain two pieces of information. So we can annotate it with some documentation saying what the package actually does. Of course, we have to write the package name. But we can also annotate it with the shared keyword. And what the shared keyword does is a shared package will be visible in the module to the clients of the module in which the package sits. And the non-shared package won't be visible, so it will be hidden. So shared is a form of abstraction. So modules. Modules in Ceylon are defined in yet another metadata file. It's called module.ceylon. And that file, again, should sit in the hierarchy wherever the module is defined. So a module is, in fact, a set of packages. And when you compile Ceylon and you compile a Ceylon module, the result will be a number of .car files or archives. Car is Ceylon archive. and there will be one for each module, right? The name of the module should be the common prefix of all the packages that are contained in the module. So again, here, the reverse domain convention should be used. And hence, all packages should start with the name of the module, right? So what does the module metadata file contain? So of course, it contains the name of the module. Like with packages, we can have some documentation, so we can describe what the module actually does. But here, additionally, we can specify the version of the module, right? So in packages, if we look at the package definition, we only had the name, the package keyword, and the name of the package. Here we also get the version number. And additionally, we can import other modules. So when we import modules, we can use code from these modules. Of course, we can only use shared classes from shared packages from these modules, right? And here we can see yet another usage of the shared keyword. So if an import is shared, it's a bit like a transitive dependency. So it will be, if anybody depends on the module we are defining, they will also depend on our shared imports. And also another thing you can see here is that the imports are checked by the IDE. So the Mongo driver is a module that I came up with, and it doesn't exist in the repository, so it's marked as an error. Okay, so there's more to the modules than simply packaging them in car archives. You can also create runnable modules. So in the module file, you can specify what is the entry point to the module, like the main class, and you can actually use the Ceylon command line to run a module. And what happens when you run or when you build, Ceylon uses repositories. So these are similar to Maven repositories. They can be both local and remote. There's a default repository called Ceylon Herd, which contains like all the open source and publicly available Ceylon modules. And these repositories are used, as I said, in two cases. So during the build, all of the dependencies are downloaded, and also when running. Right? If you run a Ceylon module and either the module is not found locally or any of its dependencies are not found locally, they will be automatically downloaded from the repositories. Plus, we get a runtime component here. So all of the modules have, each module has its own class loader. This is based on JBoss modules, which is in turn part of the JBoss application server. I guess if there's one thing that the application server team knows about, it's class loading. So they use it here as well. Okay, so summing up modules in Ceylon. So as each module system, as I said, you can group code. The modules in Ceylon are reusable, right? You can reuse them through the repositories, either public or private. You get abstraction via the shared keyword. You can abstract classes. You can abstract the whole packages. There's, again, no way to actually implement an interface with a module. You can kind of implement an interface, but you don't have any way to enforce it in the module metadata. You can compose modules, so you can compose by importing them. You cannot compose by nesting modules, so you cannot have modules inside modules. So it's like a one-level concept. You get metadata, both for packages and for modules, as I've shown. And additionally, you get the runtime component. Okay, so to sum up, modules come in a lot of different flavors and sizes. If you look at the various concepts we use in our languages, most of them can be viewed as some form of modules. And so now the question is, how many different module types do we want? Do we want a lot of small but specialized module types? Do we want maybe fewer but more general? So maybe we should be looking for some way to merge classes and packages. our packages and build modules, as Veripacks tries to do, and in fact, Ceylon as well, right? In Ceylon, a module is in fact like a top-level package, which when you build it, results in a separate archive. So here, the concept of a package and the build module is somehow blended together. And right, so when we identify what kind of modules do we want, we can then think which traits or which requirements we want each of these types to meet. And maybe it's the challenge for the next big language, which I guess will be invented someday. Okay, so a bunch of links. The Veripacks project is open source. You can take a look at it and use it today. Same for Ceylon. And again, my blog. And as an ending note, my company is developing a code review tool. If you've been on my quickie today, you probably heard about it already. So it's a code review tool made by developers for developers. So we're aiming to be a really friendly, give a really friendly code review experience. So we are also starting I am proud of my code movement. So as you can see on my t-shirt, I also have some stickers if you would like. So yeah, please come and get some. There's also a special version of CodeBrack. We are not exactly ready with the 1.0 release, but you can get an early preview version if you go to the link codebrack.com/devox. So you can download it, you can use it locally with your repository. Okay, and so if you have any questions, please come ask me right now or at the party, and I will put the stickers here. So if you would like one, please come and take it. And otherwise, thank you very much.